Okay, go ahead, Group A, please. Group A, whenever you're ready.
Okay, so we are Group A, and I'm part one, and the goal of this part is to build a reproducible training pipeline for MN, MNIST. So I standardize pre-processing and fix all training settings to ensure fair comparisons across different experiments. I also establish a baseline model that serves as a reference for later results.
Very good. Don't be nervous, eh? You sound a little bit nervous. Just relax. We are all friends. We're here to learn together. Go ahead.
Okay, so MIST consists of 28 by 28 grayscale images of handwritten digits. In preprocessing, I perform two key steps. First, I flatten each image into a 784 dimensional vector. This is because we use an MLP, which requires vector input. And second, I normalize pixel values by dividing by 255 so that all inputs fall within a range of 0 to 1. This helps stabilize training and improves convergence. So finally, I split the data into training, validation, and test sets. The validation set is used for model section, while the test set is only used for final evaluation. For model, I use a simple multi-layer perception. The architecture goes from 784 input units to two hidden layers and finally 10 output classes. For training, I use cross entropy loss and the Adam optimizer with a learning rate of 0.001, a batch size of 128, and train for 10 epochs. Here we show the baseline training results. We can see that the loss decreases over time and the accuracy improves steadily. This indicates that the model converges properly without instability. This baseline will.
Can you close the little tab for the sharing?
Oh,
yeah,
okay.
exactly. Yeah. Okay, go ahead.
So this baseline will serve as a reference for all later experiments.
This is part 2. In this experiment, we compare wide and deep neural network architectures under a fixed neuron budget. The results shows that validation accuracy generally improves as the neuron budget increases, but the rate of improvement gradually slows down, indicating diminishing returns. At smaller budgets, K equals to 1,000 to 2,000, while networks consistently outperform deep network. This suggests that wide architectures are more efficient when model capacity is limited, likely due to easier optimization and more direct information flow. However, as the neuron budget increases, deep networks show steady improvement and eventually surpass wide networks at higher value of K, around 2,500 and above. This crossover indicates that deeper architectures can better exploit larger capacity by learning more hierarchical representations. Additionally,
just let me pass a second. Because the other groups they saw that the wide was always better, right? In the last week, right? So and here the variance is sufficiently large. So did you average this over how many runs?
maybe
how many initializations?
3.
3. I think if you average more, if you average over 10, then something is going to stabilize. Because you see here that the difference in accuracy is to the 3rd digits, right? So, batch size is 128. How many images did you use in total? 6,000. How many images did you use? The whole data set?
Maybe 50.
How many? 50K?
50.
What's the data set size that you use? Did you use the full data set? Hello.
I'm not sure.
Can you check the code a second? Anybody in the group knows? Did you use the full data set for this run or? Yeah, can somebody tell me? Yeah, because last week we had that the wide ones were always better. And here you see that basically your accuracy goes down for the wide network as the number of neurons goes up, which makes no sense, right? I mean, it's not what you would expect. So the learning problem is simple, but the accuracy should saturate, it shouldn't go down. And you had 10 runs. I wonder if it's the data set. Yeah, anybody knows what's the size of the data set? Otherwise, we move on, right? Like when you load the data set, you load the full data set, yes or no? Hello. You can just show me the code also if you want. We can just go through the code together. Okay, let's go forward. Yeah? Go ahead.
Oh, okay.
Just a curiosity. Go ahead.
Additionally, error bars reveal that deep networks exhibit higher variance and small budget, suggesting that they are less stable during training when capacity is insufficient.
That makes sense, right? That makes sense.
Overall, these results demonstrate that both the size and structure of the network are critical factors in performance. While wide networks are advantageous under tight constraints, deep network becomes more powerful when sufficient resources are available.
Yes and no. Yes and no. Yes and no. It really depends on the learning problem, I think. Yeah. Go ahead.
Okay. Next page.
Yellow. Somebody go to the next page. Okay.
Okay, so now we add the bottleneck, and the bottleneck model is like making the information pass through a narrow road in the middle of the network, right? And because of this, the model is forced to keep only the most important information. And as you can see from the graph, bottleneck is not the best at every K, but it's quite stable. Its accuracy does not change too much when K increases. This means that the bottleneck structure is more balanced and less sensitive to the size of the neuron budget. And let's compare the 3 different models. So the wide model puts more neurons in one large layer. And this gives it a strong performance when budget is small because it can use the limited neurons very directly. And in the graph, Y performs best at smaller K, such as 1000. And the deep model spreads the same number of neurons into several layers. And when K is small, each layer becomes narrow. so its performance is worst at beginning. But when K comes larger, deep improves more obviously. When it increased to like 3,000, it is the best one, the best model.
So here, the depth of the deep model increases with K as well, right? So you fix the number of. Yeah.
I think so.
So you fix the number of neurons per layers, and then you get more layers, you get more neurons, right? Something like that.
Yeah.
You don't sound too sure.
I think so.
I didn't say that you lied. I said that you don't sound too sure. Go ahead.
And the bottleneck model is between wide and deep, right? And it has both wide layers and narrow layers. So it keeps like strong representation ability while also forcing the information compression. And in this graph, bottleneck is not always the top one, but it's very steady and competitive. Overall, the graph shows that the total number of neurons is not only the important thing, it's how we arrange the neurons also matters. And wide is better when the budget is small, and deep benefits more when the budget comes larger. And bottleneck is the most stable and balanced design.
Yeah, I mean, as I said, everything depends on the learning problem, right? So this learning problem is very, very easy, as you can imagine, compared to generating text images from human prompt. But yeah, it's not easy to generalize beyond the learning problem. Go ahead.
Next page.
Okay, it's my part. And on the left, we established our baseline model using a fixed MLP, and we tested spatial transformations and corruption methods and their combinations. And we could look at the table on the right. Our baseline accuracy is 97%, and only translations surpassed this, improving by 0.15%. And conversely, destructive methods like noise and erasing decrease accuracy. The rotation plus noise plus erasing combination suffered the largest drop of 1.34%. And the conclusion at this part is that aggressive augmentations destroy the essential features of low resolution MNIST digits and overwhelming our lightweight model's capacity.
So for this one here, this is average as well, right? Over 10 runs, correct?
Yes.
Yeah, so here, from my point of view, I would have stopped the training before, because, so can you go back a few slides to the accuracy versus iteration number? Can you go back? Go back. Here. So one more. So look at the plot on the, go back one more, stay there, don't move. So look here, right? So you see that the learning starts off very sharp and then it flattens down.
Yes.
And so now you're doing this test at 10. At 10, the network is fully trained, right? So if you look at the performance at that point, whether you do augmentation or not, doesn't have too much effect. But if you plot this curve, right, my guess is that when you add the augmentation, then you rise up faster. Okay, that's my guess. That's what I would like to see. Okay.
Okay.
So the network trains faster with augmentation, and then of course, if you let it go for a long time, then you will achieve the same performance. So I wonder if you will see that that you have a faster training on the earlier rounds rather than roughly the same point at the end of training. Because also last time there was a group that was saying, oh, we don't gain anything with augmentation. And I don't think they did anything wrong, but I think this is what you're observing, right? That at the end of training, the accuracy that you achieve is the same because the dataset is large enough to see all possible variations. But I wonder if the effect of augmentation is to speed up the time at which you get to the ultimate performance. Does it make sense?
Yes.
Okay, go ahead.
Okay. And yes, next page, next page.
Class imbalance, yeah.
And this test shows our experimental results. The bar chart compares different augmentation methods against our augmented baseline, represented by the dashed line. And first, the transformation is the best performance. It's the only method that surpass the baseline, and showing that slight positional shifts help the model adapt the real world of center and handwriting. And second, noise and erasing actually decreased performance since MNIST images are only 28 times 28 pixels, and adding noise or removing patches easily destroy the essential features of the digits. And finally, combinations like rotation plus noise plus erasing resulted in the lowest accuracy. This proves that excessive transformations severely distort the original data distribution, pushing it beyond the model's learning capacity. Okay, and the next page. And here's our key insights, and this is the answer of the text. And first, translation was the only method that boosted accuracy, improving it by 0.15%. This effectively helps the model recognize digits that aren't perfectly centered. And second, applying multiple transformations simultaneously didn't work well. It distorted the data way beyond what our simple MLP could handle. And third, destructive methods like noise and erasing hurt the performance in low resolution 28 times 28 images. These methods simply destroy the critical features of the numbers. And most importantly, data augmentation successfully reduced overfitting. The trend and validation gap shrink significantly, dropping from 1.25% in the baseline down to just 0.36% with translation. And this proves that augmentation effectively prevents the model from simply memorizing the training data.
So see, you see that accuracy is not always the only metric that you want to look at, right? So
Yes.
good point. Very nice.
Okay, next page. And
Okay,
yes.
I'll take it from here. And in this part, I dive deeper into the augmentation combinations, and by training the model with augmentation combinations, we found out that the validation accuracy actually is improved, but only by a very very small margin. But it does improve in these four combinations that I tried training with the model. I think because different kind of augmentation actually helps with different deficit of the image quality. So different combinations shows different improvement over the original unaugmented model. And I also tried some other combinations, but those are not quite useful as some combinations are actually conflicting with each other. So it does not really improve the end results. Next page, please. And for the per class accuracy, we found out that the 9 is the one with the lowest accuracy, and it is mostly mistaken with 7. And I think it is because that 7 and 9 can be quite similar when a 7 is not written with a dash in the middle of the digit. So I think that is why the two digits are mistaken the most. And yeah, next page. And yeah, as I mentioned in the previous slide, the most confused pair are 7 and 9. And a 9 is predicted as 7 for 8 times. That tops the chart. And yeah. Next page. Well, I don't know. There was supposed to be a part after my part. I don't know what my groupmate changed. Yeah.
Oi. What happened, guys? There is the most fun part, right? There is the one with the twin network, the embeddings. Where is that part? It's the part with the twin network, right? They use the same twin network twice. You just tell them which one is the same, which one is different. And part 6, let's see. Oh, this is part 6. What is part 6? Guys, part 6 is the most fun one, right? Come on. What happened? Guys?
I'm not sure who is pausing. His line name is B, I think.
Did you do it or not? Guys, it'd be nice to see part 6. What do you use Fusion 360 for? Hello. Group A.
I'm the leader of Group A, and I'm not sure who do this part. And
Somebody should know, right? Did you guys all present?
we still have one member, and I'm not sure if he's here. He said that he wouldn't be here last time, so. But I think.
That's why you want to go this time, right? Yeah.
I think maybe he's here now. I'm not sure, but I don't know his name.
Okay, then we move forward. Yeah. Okay, very good. Group E, tell me. Go ahead, Group E. Hopefully, Group E can tell me.
Okay. Hi.
No, Group E. Wait. Hi.
Let me share my.
Try to fix your microphone a bit since the volume is going up and down a little bit randomly. Okay, whenever you're ready, guys, go ahead.
Okay, so can everyone hear me talking?
Yes, we can hear you talking.
All right, so hello, we are Group E, and today we are going to explore the efficiency of neural network architectures using the MNIST dataset. The MNIST consists of 7 70,000 grayscale images of digits 0 to 9. And in text 0, we split data into 70, 10, and 20 for train, valid, and test. And we fixed the redundancies for reproducibility. And we use Adam optimize cross entropy loss and trend for 50 epochs. We tested how a network's shape impacts performance under a strict neuron budget K. 3 families were defined, and the first one is wide with 1 hidden layer, and deep 4 equal layers, and bottleneck 4 layers with 40-10, 40-10 distribution. And we tested 40 budget points from K equals 300 to 3000 with 5 independent rounds each to ensure the stability. The result shows that the wide architecture consistently dominated. While small K models struggle to learn, the wide family reached a peak validation accuracy of 97.81 at K equals 2,800. Notably, its stability is superior. And at K equals 1000, it already outperformed the peak results of both the deep and the bottleneck families. Also, we can also note that the bottleneck architecture benefits the most from the increased K. And we also observed that there's a diminishing returns effect. Increasing K too much provides marginal gains while increasing costs. The wide architecture excels here because the ambient features are simple geometric strokes that can be captured in a single layer. However, since it lacks hierarchical features and instructions, it will likely to collapse on complex datasets, which require deep structures for the high-resolution color data. And in the end, in conclusion, for lower budgets like K under 1000, the number of neurons is critical for overcoming the underfitting. Here we can observe the result. However, at higher scales, the choice of architecture becomes the most deciding factor for peak performance and stability. For simple image text, the wide architecture remains the most efficient and stable one. All right.
This table summarizes our core findings on data augmentation. It tells how different transformations affect the network's generalization. It documents the augmentation type, validation accuracy, and the exact approval against our baseline model. We compile this data to answer 4 critical questions. Which single augmentation improves performance the most? Do combinations work better? Do any methods hurt performance? And finally, does augmentation reduce overfitting? And look at the results. The conclusions are clear. First, translation was our most successful method. It yielded the largest improvement of 0.002. Our combo method did not outperform single augmentation. Methods like scaling, erasing, and the combo itself actually for validation performance and showing negative scores. This suggests that excessive transformation might destroy critical digit features. And finally, regarding overfitting, we saw a massive success. The baseline model memorized the training set with a perfect 1.0 accuracy. However, every single augmentation method broke the
memorization and droplet memorization. They double training accuracy and narrow the gap with validation accuracy. Uh, this proves our argumentation works. Instead of memorizing the data, the network learn more generalized features. And next page. And this bar chart compares with the validation accuracy of each method. The red dashed line represents our baseline at 0.9783. This feature benchmark makes it instantly obvious which methods help the model and which method works. This chart answers our first three experiment questions. First, translation provided the largest improvement, boosting accuracy to 0.9806. Rotations also gave a slight bump. However, answering our second and third questions reveals a surprise. Our combo method did not outperform single argumentations. In fact, scaling, random erasing, and the combo method all dipped below the red baseline. They actively hurt the model's performance. The key takeaway is clear. Gentle geometric shifts like translations help the model generalize. But over aggressive deformations or stacking too many argumentations can destroy critical digit features and confuse the network. Oh, next page.
Guys, you really need to invest on your microphone. Jesus, your microphone quality is so shitty. Try to get closer to the mic, please. It's really hard to distinguish what you're saying. Go ahead. It's so noisy, so clippy. Go ahead.
Oh. Let's look at the trend versus validation accuracy gap.
Okay.
This chart measures the model's generalization capabilities. It plots the exact difference between training performance and validation performance. Here, the lower bar means better generalization. We create this to answer a crucial question. Does data argumentation actually reduce overfitting? Does this stop the neural network from memorizing the answers? Look at the graph. The answer is the resounding yes. On the far left, the baseline model has the highest gap, over 2%. It memorized the training set but struggle on new data. As you move across the chart, every single argumentation technique successful shrinks the gap. Translation, for example, brings the gap down to almost zero, showing excellent generalization. Since our combo method on the far right produces a negative gap, this indicates extremely strong regularization. The training images were so heavily distorted that the model actually performed better on the clean validation set. This chart proves that data augmentation is a highly effective tool for preventing model overfitting. And next page.
It's very nice, right? It's very nice that you pay in accuracy, but then the gap between validation and accuracy and so you paid in accuracy, but the gap between validation and train falls. It's very nice. Very nice. Go ahead.
Okay. For task 3, I do additional experiments for text2 and use the best performing model from it as my baseline model. From the augmentation experiments, the best combination was rotation, translation, and erasing. I found that the combination with erasing is much higher than others. I think because it can it can it can it can prevent overfitting. The validation accuracy of it is 0.9832. So in this test, I directly use this model as my base model for further analysis. Okay, since test 3 focus on class-wise error analysis and the data imbalance, I should not improve or modify the model itself. So, okay, next page. Oh, on this side, I analyze the model's performance for each digit class on the test set. The bar chart shows the per class accuracy, and the red line shows the error rate for each digit from 0 to 9. Overall,
I think the model is too good, right? The model makes no mistakes, so you have a 98% accuracy. So I think maybe you should have taken a worse model, right? So now you see no difference. Go ahead.
Overall, the model performs very well on all cases.
Exactly.
With accuracy close to 98% or higher. However, some digits are still more difficult to classify than others. From the result, the top 3 hardest digits are 7, 9, and 8. Digit 7 has the highest error rate, about 2.43%, with an accuracy of 97 and 0.57%. Digit 8 is the second hardest, with an error rate of about 2.26%, and digit 9 comes next, with an error rate of about 2.18%. A possible reason is that these digits have relatively more complex or variable shapes. For example, digit A contains 2 loops, so it is hard handwritten form can vary a lot. Digit 7 and digit 9 may also look similar to other digits in some writing styles, which increases the chance of confusion. So although the overall model performance is strong, this class-wise analysis shows that the model is not equally confident on every digit class, and digits 7, 8, and 9 are the most challenging ones. Next page. And this slide shows the confusion matrix of the model on the test set, which help us understand which digit pairs are most frequently confused. Most of the values are concentrated on a diagonal, which means the model correctly classifies most test samples. So overall, the classifier performs very well. However, if we look of diagonal entries, we can still find several confusion patterns. The most frequent confusion is between 7 and 9, and also 9 and 4, with count of 11. The second most frequent confusion is between 5 and 3, with a count of 10. We also observe other notable confusion pairs, such as 8 and 9, 4 and 9, and 7 and 2. These errors are reasonable because many of these digit pairs are visually similar in handwritten form. For example, 4 and 9 may share a similar upper structure, and 5 and 3 can look like when the handwritten is curved or simplified. Also, 7, 8, and 9 were already the harder classes in the previous slide, so it is naturally that they appear more often in these confusion pairs. So from this confusion matrix, we can conclude that models mistakes are not random. They many happen between digits with similar visual patterns, which suggests that handwritten style still has a strong influence on the classification errors. Next.
G is very dense. Go ahead. This is the class imbalance. Okay, very good. Yeah.
And then in this second part of text 3, I introduce class imbalance into the training set in order to study how data distribution affect learning. Based on the result from part 1, I chose digit 7, 4, 7, and 8 as the affected classes because these classes are already relatively difficult or close related to confusion pairs in the confusion matrix. Then I created several imbalance scenarios by reducing their training samples to different levels, 50%, 20%, 10%. The table at the top summarizes the per class accuracy under each imbalance level. The two plots below visual the trend more clearly. On the left, we can see the accuracy curves for all classes. Most unaffected classes remain relatively stable. And however, the affected classes show clearly performance drops as the amount of training data is reduced. On the right, I zoom in on digits 4, 7, and 8. Among them, digit 8 drop the most when the data becomes severely imbalanced. Digit 7 also declines noticeably. In contrast, digit 4 remains relatively high even when its training sample are reduced. This suggests that different classes do not respond to imbalance in the same way. Some classes are more dependent on having enough training examples, while others are more robust and can still be learned well with fewer samples. Another interesting observation is that some classes that were not directly reduced may still be affected. This may be because similar digits share visual features, so weakening one class can also influence how the model separates nearby classes. Overall, this experiment shows the data distribution has a direct impact on class-wise performance.
Very good.
And especially clear for visual confusion classes. Okay, this is the end of my.
Good job. Good job.
Okay, so for task 4, we're using a twin model, which is to enter 2 objects into same network architecture and get 2 embeddings. Then we'll compare the 2 embeddings to see if these 2 objects belongs to the same group or not. So for the definition of loss here, we followed the suggestion in the challenge, and we use contrastive loss, which is defined based on the Euclidean distance of the two embeddings. And for the network architecture, we try using the convolution network here, which is which content of 2 modules. Each module is a string of layers that is a convolution layer, a batch to learn layer, a ReLU, and then a max pool. And so this would turn the 28 by 28 pixel digits after 2 times of max pools into a 7 times 7 size embeddings. And for generating positive pairs, which is pairs of indices that contains 2 digit picture that is actually the same digit, and the negative pair, which is 2 indices that compare digit pair that is different digits. The way we do it is first we create a dictionary object that contains the indices of all digits, and then we randomly select first digit and whether 0 or 1, which is we're generating negative pair or positive pair. And if it's 1, we're generating positive pair, then we will select 2 indices from that dictionary object of that digit. And if it's negative pair, we would randomly select another digit, and from that indices pool of that digit, select 1 indices. To be honest, this is not the most perfect method. We will see in the following results that these methods of generating negative and positive pairs have some limitations, and we'll cover it later. And
Okay.
for the dimension of embeddings, we've tried 2 and 16, and we can see from the plot of loss versus epochs here that with higher dimension of embeddings, we can achieve lower loss, and the models converged quicker. And then we conducted the principal component analysis and the TS.
I think the, do you want to move to the next slide? I think we didn't see. This is the curve. Okay, this is the curve that I'm going to see exactly. So encoding 2, encoding 16, 0.07, blah blah blah. You go down 15 iteration, train validation, and train validation. Okay, go ahead.
Yeah, we chose 15 epochs here to remain using 15 epochs as the previous text. And then next slide. Okay, so we did principal component analysis and TSNE clustering, and for dimension of 2, we felt that because when doing PC analysis, it's easier to visualize this when there's only 2 components, because it's a 2D visualization. So
wait a second. Wait a second. Why are they in a circle? Did you restrict the embedding to be unipower?
Sorry.
Why are the points on a circle? Why are the points just drawn on a circle?
I think that's because the embeddings are normalized as projecting it to a sphere. So I think that's why the PCA clustering looks like a circle.
Usually because you normalize. So when you normalize, I'll try to say it as clear as possible. I think I understand the mistake, right? So here, when we normalize, we do. So basically, the normalization, let's call it just C. Okay, I'll write it in chat. C is equal to 1 over the sum over the data set. I'll write in chat, right? Data set times the let's say the norm of y square. Okay. But I think what you guys did is that you did C equal to 1 over the sum over the 1 over the over this just y over this over y. Correct.
Okay.
So you see that. So usually when you normalize, means that you take the variance over the whole data set, and you make the variance equal to 1. But here you didn't take the norm over the whole data set, but you normalize for each data point. Is my guess correct, guys? Yeah, just look at the code.
I think I need some technical support here from my teammate. My personal guess is that I thought I didn't really check if this logic was correct, but I thought it was because the PCA components here use is 2, and if you normalize for x and then you normalize for y, is kind of like the linear algebra way of showing indexes on a sphere. So that's why we're seeing a sphere, but I'm not sure if that's the same thing.
Because here you see that the issue is that basically here you only have one unknown variable. You only have one dimension, which is the angle, right? So even if your dimension is 2, you actually the information is containing one parameter, which is the angle. Right, so you removed the magnitude of the data of the output. Yeah, so there is some. Yeah, there's something there because your modulus is 6 to 1, and the PCA doesn't fix the modulus to 1. I mean, it doesn't change the. I mean, the result is still there. Right? You still see that there is a separation in the angular domain, so it's okay, right? So the thing is that I just need to know if you did this normalization during training as well. Can you check if you did it during training?
Okay, one second.
Yeah, check. Because basically, right, there are plenty of embeddings that are embedding of a sphere. No problem. I just want to understand if you did the normalization before training or during training or after training. It seems that it was during training because when you collapse the embeddings to the sphere, then you still have a very nice separation. So you can just show me the code. We can go through the code together. No problem.
Okay, so can the guy sharing the screen switch to the collab notebook we use?
Let's go through the code together, you know. Dun, 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 dun. And he just left class. He just left the meeting and walked away. No, I'm sure that, yeah, I just want to, it's just interesting for me. Very nice, very nice. You still have to tell me why you think that your choice of selecting the elements was not good. Huh? You have to get there. So this is the Siamese NLP. Forward, stay there, batch. Okay, good. Go down. Then you go to the training loop. Classify, data comes later. Result. Go to the loss where you do the loss calculation. Huh? Evaluate. So it is already trained. And there should be a point where you have the output of the network, which is Y, right? Train, okay. It should be a criterion train loader there, console history. Optimize the current loss, time, model evaluation loader, plot, plot embeddings, TNE, I see, I think, okay. Can you just show me, so there should be a point where you have the output of the one network, then you have the output of the other network, you calculate the loss there. And the loss where there should be the margin classifier. Let's go to that one there. Over the batch. Go down a little bit. Go down. Random choice. Okay, so means MLP. Okay, so this is the network. So this is not conv, right? This is not a convolutional network. It's only linear. Go down.
I think the reason is that actually there's only 4 texts, but there's 5 people in our group. So there's 2 people who tried doing text.
I see.
And this is not,
this is the
the code we're showing. We're explaining during our presentation. This is another try.
I see, because here you use cross-entropy loss. Okay, good. Can the guy that did the margin, arc margin pro, stay there, arc phase, stay there. Model is the same history and auto dimension is equal to 2. Then you do arc phase. What is this arc? Arc margin product. What is this arc margin product? Can you find this function? Feature scale margin weight parameter. This is the initialization. So okay. And then what comes out from arc face goes into there. So you optimize the parameters of the network plus the margin classifier, okay? And then you have a cross entropy loss. And then it just stay there. Cross entropy loss, Siamese missed. So you also optimize over the so much. Okay, very good. Then show me when you visualize the embedding. Show me when you visualize the embedding. Let's see if you normalize there. Plot embedding, blah, 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 blah. It's embeddings. Plot embedded TNC. Stay there. Fit transform embedding. What is this fit transform? Yeah, just show me the fit transform and then we'll have. Yeah, no, this is a TNSC function, so you have to look and you have to go online. Open another tab and check on the tab. Yeah, it comes from the TNSC, yeah. And then choice subset, no state, it's TNSC. Yeah, let me just check. TNSC fit transform. Yeah, just the training TNSC fit transform. Fit transform. So what are the parameters there? Okay, got it. Components 2, perplexity, random state. Okay, good. Okay, we're good. Okay, go ahead. I got it. Okay, I got it. Go ahead. So the blah, 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 it's separated. Okay, good. It's all fine. Yeah, go ahead.
Okay, so after my part, there will be presentation of another group member who also did tests and whose script was showing just now. And
so, but why did you tell me that the selection of the pairs was not efficient? Why did you say that the random selection was not efficient? Go ahead.
Oh yeah. Okay. So for dimension of 2, we redo the clustering to see if the labels we retrieve from the embeddings is actually matching the true labels, and I feel like you can see it pretty obviously from the 2+. They're pretty similar, and we can retrieve which digit is the cluster ID corresponding to from counting the largest class in each cluster. And next slide, please. So we also did the confusion matrix and some of the clustering in statistics here, and it shows that the model did fairly well, and we can also observe some of the conclusions from text 3 here as well. For example, the mix between 4 and 9 is also observed here, and another common mix in text 3 is 7 being predicted as 9. It is also observed here. So now we know that a network can recover information from pairs information only, and samples from the same digit label do cluster together. And then we look at apply the same protocol to dimension of 16. Can you go to next page, please?
Nice.
Okay. So on the left is principal component analysis, and on the right is TSNE clustering. And I feel like it's pretty obvious that TSNE performed better. The clusters are very separated, and the true label, like when you correspond them to the cluster ID, you can see they're referring to the same digits, even though the colors randomly assigned are not the same. And the PCA here, perhaps because there's only 2 components used here, but there's 16 dimensions. So according to the code results, the explained variance is only 51%, which is not very ideal. And another thing why I say that this mechanism of generating pairs is not perfect, because you can see that 8 is obviously smaller than other clusters. It means that the class of 8 is actually imbalanced in this pair selection. So in the pair selection mechanisms, I did not consider how to ensure that all digits have similar similar portions in the pairs. But it seems that the models performed too well that it did not affect the accuracy a lot. So next page, please.
Wait. Let me ask you a question.
Oh,
Let me ask you a
sorry.
question.
Okay.
Because from the way you express yourself, I want to make sure that we're on the same page. So when you do k-means, you can do k-means on the original 16 dimension. You don't have to do ECA down to 2 dimension and then do k-means on the 2 dimension, right? You could also do. Okay. Good.
Yes.
Go ahead. I just want to make sure that we're on the same page. Go ahead.
Okay, so we also did the confusion matrix here, and we can see from the accuracy and the pairs being mixed that the dimension of a 16 perform better than dimension of 2, as we've seen earlier. And the larger mix here seen is 9 being predicted as 8. I think this is likely due to 8 being there's less 8 in the pairs, so that's why it's not 4 and 9 or 7 and 9. The other mixes we see earlier, but it's 8 and 9 here. But in general, with higher dimension, we can get better performance. I think that is the end of my part, and then another member will explain another way of doing task 4.
So that's what I have to learn, right? So if the number of tasks is even and the number of members is not a multiple, right? Then the multiple students are going to do the same task. I should keep that in mind. Go ahead.
Okay. And in my part, I compare 3 different types of models: full cognitive based, CN based, and multi-head cell attention based. And I control the all neuron number with about 2,800. And I tried 4 kind of dimension, 2, 4, 8 to 16. Next page. And this time we use arc phase to other doors to judge the embedding.
That's very nice. Right? So the margin is it's on the trigonometric. I mean, it's a trigonometric function. It's very nice. I didn't know that you could do this.
If the input should be normalized before this layer, if the label is the two embedding have the same label, then the angle should be 8 m. N represents margin.
Okay.
Then compute this cosine value. Will multiply together. Then we compute its softmax loss.
Next a second. Let's stay here a second.
Next page.
Stay there. Let's go back.
I'll go back.
They do the contrastive loss, right? The margin is on the trigonometric function, right? But they have they do it on the trigonometric domain, right? I want, because of course, whatever Gemini told you this, right? I just wonder why he prefers this spherical type of dimension instead of the margin on the Euclidean, right? I wonder why this was the embedding that it induced. So it induces the embedding on the sphere, right?
I want to try to use cosine similarity of the 2 embeddings.
Yeah. But usually you do that if you're doing, let's say, NLP, right? So in NLP, usually you do this cosine similarity, right? But here it's I would just use L2 distance because they're doing MNIST, so they're doing with MNIST, they're doing the contrastive loss to say if 2 digits are the same or are different, and then they do k-means. And I wonder why ChatGPT told, I mean, whatever, why GenAI told them to use like a spherical embedding. Yeah, because of course, if you go on higher dimension, right, then the cosine is applied component-wise. So on each dimension, you have a circle. right?
Right. Yeah. It will be on the circle, the emitting field on the circle.
I mean, on one dimension, it's a circle. If you have many dimensions, then you have a circle per each dimension. Don't think that you have a sphere, right? You don't have a sphere. It's like you have a geometrical thing where, like if you were in 2 dimensions, right? It will be a circle in this dimension, a circle in this dimension. So you understand what I mean? Like independent dimensions.
Some features will tell you it's similar, and some features will tell you it's
But it just forces them on the sphere. Yeah. It's just interesting for me because, of course, as I said, Jenny, I told you to do it, right? And I'm just wondering why you went to do this way. Go ahead.
something's gonna break.
Something's going to break at some point. Go ahead.
Okay. Why I choose ArcFace? These are 3 reasons. And the first is, since we add a margin between the same class, so we repel the 2 same class, left a margin between. So different from the distance loss, it will converge more faster. And the second one,
So the trick that you use also when you have SVMs, right? Also in SVMs, you have a certain margin, right? So this trick comes from support vector machine. Did you do support vector machines? Did you study support vector machine, SVMs?
oh, I know what it is. SVM.
Did you study before? Or?
Yes.
Okay, so this trick of the margin comes from SVMs. Go ahead.
This is just a kind of SVM, but in severe. The second is enhanced separability, since it left some margin between the 2 different classes. And while standard softmax shows separate class. And the third one, it is independent of data size, which when we use distance loss, we need provide 50-50 positive and negative cases. Next page. And compared to these 3 architectures, we'll see attention network is hard to convert, but full connected based model converge fast. Next page.
Stay there a second.
Okay.
What is MHSA?
Multi-head self-attention.
I mean, it's got the MNIST. Where did you find the multi-head self-attention?
Since I've learned so many models before, I want to compare the different architecture.
Okay, but you understand that this is MNIST, right? So this is a linearly separable data set, right? So you will wait until at least I give you CIFAR 10, right? Don't put multi-head attention on the code. Sorry, guys. Don't put multi-head attention on the freaking data set that is really separable, right? So you're going a little bit overkill here, right? Okay, go ahead.
Next page.
Yeah.
Among the 2 projection method, I think the TSNE has better performance since it is more easier to visualize. So we will use TSNE to show. Okay, next page.
Again, so going back to the comment before, so I agree with you guys that TNSC does better, but of course, TNSC has a certain cost, right? So PCA is extremely fast. You don't have to think about it. It does a linear separation. I understand that TSNE does better, but again, so there is a complexity trade-off here, okay? So just don't forget. Go ahead.
PCA is fast. Okay. Next page. In the 2 dimension, since it is a circle, so it is hard to see what the number it is on the plot. So next page. When the dimension reach 4, it is we can easily see the result of the clustering. These three models all doing well on this test. Next page. And so does the higher dimension. You will see CNN based and attention network is result see like a ball, but full connected, the result is like a worm or banana. It is a fun fact. Next page.
I would say that sausage, as being European, I've seen more
sausage.
banana. Just joking. Go ahead.
We use C-rate score and AI score to show the ability of clustering. We'll see the full connected is much better than the other. So I conclude full connected network does better in this simple test. The test is too simple, just 28 square.
But here, did you keep the number of parameters the same? Because you cannot have did you keep the parameters the same? I don't think so, right?
Yes, I keep the parameters same.
Also, you're fully connected. Your CNN, then it has a ton of layers, right? Because the CNN consumes very few layers, right? So it must be a very deep network, right?
Since its neural number is constrained in 20,800. So
you know what I mean, right? Because the convolutional network has very few parameters, right? So if you have to use all those neurons, then you have to have many layers, right? Oh no, you stack them. Okay, so you stack them. So you have you have a lot of convolutional kernels. What's the depth of the CNN then? Three layers, 4 layers? How many layers in the CNN?
How many there? Just 2 convolution layer. Since we don't have much, we don't have many neural numbers.
Understood. Okay, go ahead.
Okay. Next page. Also, let me simply recap the arc phase. We use import separation between different classes. And when visualized, TSNE is better to see. And overall, the task full connected always doing better than the others like signal and depth attention. Okay. Thanks everyone.
I see why they let you do this part by yourself, right? Because you want to go crazy doing multi-head self-attention and embed this on the sphere. They were like, let's let this guy go. He's an overachiever, He's a okay, very good, guys. Let's take a 4 minutes break. I see you back at 3:03. No, what am I saying? At 43, 44. Go walk around, drink some water. Then we do CNN. Okay, we do a class in CNN, and then we all go running together. Okay, I'll see you back here. Hello, guys. Any questions, any comment? Hello, guys. Hello, guys. Okay. If there is any question, otherwise we go ahead and we do a little bit of CNN. So let me just share the slides that we're going to use. So now we use the CNN slides here. So we move to this other set of slides. I'll post on Slack. Hop, 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 hop. Here. Channel slides for the next few classes. Yeah, let me know if there is any question. We start soon. Because some of you already did CNN, but I suspect that there were some details that you missed, so we can do it in class. Okay, good. Any question, guys? I'll give you 1 minute to ask question, otherwise we start. Let me get some water. Okay, good. As always, we will say thank you to our friends at Harvard for lending us the slides. Good. So the last group already did this. So another structure that people often use, especially when it comes to image processing, are convolutional neural network. Some of you might already seen the convolution as a basic operation when it comes to linear system theory. And in fact, the operation was borrowed by the people in machine learning and AI to develop their own specific architecture. Very easy to code, right? Some of you already seen this. So this conv2d is the layer that you want to call. So you have to ask yourself, why do you need to know anything else, right? So you just put in the code, you just add your cloud code to do the convolutional neural networks, and job is done. But of course, we hope that by understanding what is happening under the code, then we can do a better job. And from my point of view, I'm trying to convince the students to pay attention to these aspects of problems, so they don't just vibe code throughout their whole life. But it's a futile attempt. Okay, so remember, let's go a little bit of the motivation. So we discussed how we take this fundamental approach in which we say that the response that we observe, it's a function of the input plus some noise. And the algorithm that we choose embodies a certain set of function f. And among this function f that we can parameterize through the problem parameters, we hope to find the f hat, which is the closest one to the true f. Okay, so the idea is that the reality gives us a true f, right? And the real world gives us a function f that really maps the input into the output, and we approximate this with a function f hat that we can implement to a deep neural network. Okay? This is the scope of this class. And the idea is that we like to work with DNN because they scale very efficiently, and they're very easy to train using backpropagation. So in a sense, we have a hammer, right? And we're looking for nails. We have a very powerful hammer, which is a deep neural network that can be trained very efficiently on a computer that we can buy very easily at a store close by us. And on the other side, there is the nail, which is the specific physical instantiation of a problem that we observe. And and we had the discussion, right? So let's say that we take let's say that there is a true function, which is this function here in the red. Then we have a bunch of observations through this function, which are affected by noise. And so this observation will correspond to these empty dots. Then what we can do is that we can try to construct different models that approximate this function. And here in blue, we see an MLP, and in black, dotted black, we see a linear model, and then we can ask ourselves, which model has the best performance according to what is permissible to us to use as an algorithm to implement this. Good. So remember the last time we did we discussed a few ways in which we can train a deep neural network. We said we can have norm penalties on the weights, we can do early stopping, we can do determination, we can do sparse representation, we can do dropout. And a few of these things, you already saw them in the challenge for this class. Some others you're going to see them in the challenge for the next class. Basically, MLPs, they are very parameter intensive, okay? So you understand very well when you're doing the coding, right, that an MLP is it's a fully connected network, right? So there is a connection between each neuron in one layer and each neuron in the other layer. And intuitively, right, the number of weights is the square of the size of the layer. And so if you have let's say if you have 10 layers, each of size 10, then then you have 10 squared, 100 multiplied by 10, which is 1,000. So 1,000 neurons to have 10 layers, and this is not desirable particularly. Like we will have to have a more advantageous scaling of the number of parameters with the depth of the network. Okay, so we have this intuition that at each layer of the network we are processing the information, we are doing some transformation which is meaningful. As the problem gets hard, we know that we have to have enough space in our parameter set to encode various informations that we have extracted from the previous layers. So we want to have a very deep layer so that we can do very deep processing, and having this scale or the scaling of the number of parameters is not particularly advantageous. And another thing that we want is a certain property specifically to images, right? So as you saw, MNIST, the best augmentation you could do was the translation, okay? Because you saw in MNIST that depending on where you place the letter, right, the MLP needs to be able to see the translation in order to do the right classification. And this follows from the fact that the processing of the MLP is not invariant translation of the input. Okay, so we identified these two particular drawbacks, and now we want to come up with a new architecture, right, that still falls into the standard machine, the deep learning framework that we have developed so far, but is able to address these two drawbacks of MLP, a better scaling of the number of parameters with the depth of the network, and invariance in the input. Okay, so here the number of weights, so let's not go through this. So on the next data set that we're going to see next is CFAR 10, right? So this is a data set of 32 by 32 color images. And this is colored, so we have 3 different colors to encode all the different channels. And the discussion is that if we had a deep neuron, if we had a fully connected layer, for each neuron, then the number of neurons that you will need to do the processing will grow. Will go in the order of hundreds of thousands very quickly. And this is what the last student was doing in the last assignment, right, in task 4 group E. He was the guy who was Bill Gates in this picture, and I was what's the name of the guy? The millionaire. Buffett. I was Warren Buffett, you know? And he was using a very complicated tool to do a simple linear regression problem. Okay, so even if we ought, you know, so we want to do something more efficient. So we want to do some feature extraction and model selection. Let's just move forward. So we know when we do image analysis, we want to be able to extract shapes, right? And the shape should be invariant to the position of the network. Yeah, some nice example with ducks and with geese. And so the idea of detecting features is actually was there way before we had machine learnings. And when we were only doing machine learning in image processing, right? We figured out that there are many different filters that one can use in order to extract edges, to reduce blur, to increase contour, and these features came from this idea of convolution. Okay, so let's try to dig here on what is a convolution. The convolution is as follows. So you take a certain area, right, which we'll call the kernel, and let's say that this kernel is a 4x4 kernel, right? So here we have an 8x8 image, okay, and this 8x8 image we're gonna scan it, right, with a 4x4 kernel. Okay, so we're gonna scan 4x4 pixels at a time, and for each of the different positions, we're gonna do a certain operation we're gonna see next, and then we're gonna move around our kernel, right? So that for each of the possible position of the kernels, we're gonna have an output of the filter, and this is going to guarantee us that no matter where a certain position, certain set of features occur in the image, then we're going to be able to scan it. Okay. So this is what we're going to do. So we're going to take the 4x4 pixel that we have, and we're going to introduce this into a neuron, and this neuron is going to take a linear combination of, and then spit out this linear combination after applying a nonlinear activation function. Very good. So this is how you imagine it, right? So there is this set of weight, okay, and these are the weights of the kernel, or it's also called the convolutional filter. And then this kernel is applied to 1 pixel at the time of the image, which means that we take the target pixel plus the surrounding pixel according to the size of the kernel of the convolution, and then we're gonna apply the linear combination as we do for 1 neuron, and then the nonlinear function. So let's do a step by step. So many visual analysis here because it's kind of hard to understand how this operation is performed, right? So, but you see how it goes. Okay, so let's say that, for example, take this. Yeah. So this is, yeah. You imagine, you see how the imagination goes. So you imagine that you rotate around the target pixel and then you repeat this operation, position by position. So this operation, it's known mathematically as a convolution, and it's indicated with this star sign. Right? So if somebody gives you a vector f and a vector g, then the 1D convolution, okay, the 1D convolution is indicated f star g of t, and it's the integral of the function a multiplied by the function t minus a, and then you integrate over a. So what is the idea? The idea is that you have, imagine the two vectors have two sequences. What you do is that you first flip one, then you shift to a, then you multiply them together, and then you integrate. Okay? So you guys are going to study this operation and many different classes. And you're going to do it in signal system, in image processing. So I don't want to spend too much time here. What do I want to tell you about this function? So this function is fundamental in the Fourier transform. Okay, so whenever you see the Fourier transform, you're going to see this operation of convolutions being a fundamental operation here. This is the version for 1D. So if you have to do the version for 2D, then the shifts will be in the X domain, in the Y domain. And it has a lot of correlation with the correlation operation side. And then if you're studying statistics and you see the moment generating function, this operation also occurs in the moment generating function, right? So the sum of two random variables has a distribution, which is the convolution of the PDF, which correspond to the product of the moment generating function. So this relationship, it's also very statistics. And there are a few books that are written about this operation. And, yeah, so you hopefully you're going to see it multiple times. You're going to have time to understand it better. And just note that for the purpose of this class, all these studies left to your own personal time. So just be aware that it's a very fundamental operation beyond how we use it in deep learning. Okay, so going back a little bit to the history, right? So before there was machine learning, people in image processing, they already understood that this the convolution was a very important operation because it could be used to extract particular features of an image that corresponded to some semantic meaning. Okay, so for example, if you take this kernel, which is a net detection kernel, and you take the convolution with this image, you see that the result of this would be to trace out the edges of the image. Okay, so intuitively, right, what you do is that you take 8 to be your center pixel. So there is a certain weight that you assign to the pixel in the image, and to this you remove the intensity of all the pixel around this pixel, right? So in a sense, if you are at an edge, right, then there is going to be a lot of variation in around a certain pixel, right? And this has the effect of contributing negatively to the original pixel, and so that's why your pixel goes a very low value, so it becomes white. Wherever if the value around you is almost constant, then these other -8 are going to send you to a zero, to a very low value, and so you're going to be almost black. Okay, so people spend a lot of time trying to design kernels to obtain this. There are certain specific feature, and people will write papers about this type of set of values and what were the properties. And machine learning did it so that we could just simply train a deep neural network and figure out which kernel we should use for a certain property. Okay, that's another filter for sharpening, right? Don't ask me to interpret this because you don't have any clear intuition. Well, I mean, it's clear that here, for example, the pixels that are the furthest away, they don't play a role, and you just take the pixel there. Just to add something, right? So when you represent an image in a computer, it's represented with 3 channels, RGB, right? Red, blue, and green. And then you sum them up together. So when you apply this filter, you apply it to each of the different layers separately. Okay? Good. So now we understood what is happening here. And then we have this convolution operation, and then we have to add a certain nonlinear activation function. Okay? So this filtering is a linear operation in 2D, of course. And then after this, we have to apply a nonlinear activation function. And then the idea is that we will stack multiple convolutional filters onto the same image, and we imagine this to be depthwise, okay? Meaning that the network is going to go into multiple layers. And if you have a conv layer, you imagine that the convolution layer has many filters stacked in the, let's say, in the z-axis, right? Just in your imagination. The y-axis would be the input. On the x-axis, on different values of x-axis, we stack a different layer. On the z-axis, we stack the filters. So if you have a certain image, you can apply multiple convolutional filters, and each convolutional filter is going to produce an output, and then there's going to be an operation which we call pooling, which tells you how do you combine the result of multiple filters that have been stacked together. And why do we want to have multiple filters for a single image? The idea is that we want each filter to specialize onto a certain feature or to a certain semantic extraction, right? So for example, here we could have a feature that extract a horizontal line, one that extract vertical lines, ones that extract circles, and then these features, they're all transmitted down the downstream neurons, and then the neurons are going to decide how a certain image is connected to a certain object is connected to a combination of features. Okay. And for example, in layer 2, we could have that we combine horizontal line and vertical lines to understand angled lines. And then it's possible in other features, we combine the horizontal and vertical line in order to understand what a rectangle is. And so we have this idea that multiple layers will combine the information arising from these convolutional filters, and then it will produce some semantically meaningful output. Okay? So in general, CNN, it's a very smart idea because, as we said, it's applied pixel-wise, so it's invariant, and also the number of parameters is very small. Okay, so you can see that a kernel, let's say one kernel is specified only by a subset of values which has no relation with the size of the image, right? So if the image is size 1,000 or 1,000 times 1,000, your kernel could still be a 4x4 kernel. So you can have this very low complexity object that produces a global result for the much larger image. Okay? Good. So as we said, we imagine CNN to have multiple channels or filters which are stacked in the depth of the network, and they're also called kernels. Okay, and this filter generally produce a translation invariant feature. Yeah, some more images here. So this is showing that. So the downsample imaging, right? So the idea is that the filter, right, is going to move of a certain stride. So it's called stride. So the filter is going to move over a certain stride. So depending on the stride, you're going to have a dimension of the output, and we have to decide what happens when the filter moves beyond the edge of the images, and of course we sometimes want to have a filter that goes beyond the pure edge of the image, so that the part of the image. A part of the filter is applied to something which is outside of the image. And we have to decide what to do with these pixels. Of course, we can stuff them with 0, or we can stuff them with 1s, or we can stuff them with some random numbers. And this is part of the challenge of this. Okay, so you can see here that you could have a full padding, meaning that this is your filter. You see the filter is very large, and when you go beyond, then you just assume that, so this is the original image, this is your filter, and this is your output, okay? So once the filter is shifting around the image according to a certain stride, which we're going to discuss later, if the filter is outside the pixels of the image, then you have to decide what to put outside of the edge. And you can measure that you put all zeros, or you can put some other random number, okay? So as we said, so the stride controls of how much the filter shifts from one step to the next. Okay, so if the stride is 1, then the kernel size in this case will be 3 times 3, and you see that we're going to have one input for each possible stride, and the stride is going to be 1 by 1. And when you get to the end, then the filter is going to shift down on one stride and then shift left of stride by stride by stride. Okay? So the red will correspond to the filter applied to this size of the image, and then the green is going to be applied to this image. And then when you go down, right, then you go down, then the filter is going to be shifting down on a certain stride. And if the stride is 2, then you shift the filter of 2 pixels right, and then 2 pixels down when you change from. So you see that this is the green, this is the red, and this is the green, right? So original, shifted of 2 right, shifted of 2 down. Okay. Now, if somebody tells you that they have a certain image which has certain width and depth, and you have a certain stride, then you have that the output side is going to follow this formula. Here there is an S missing. Okay? The stride is the meter is the stride, and this just follows from some simple math. Okay. Okay, so now we can see what happens here, right? So this is your image. Each image is composed by a layer. Each layer is applied over a certain position of the image according to the stride. And don't forget the RGB image. So this is a black and white image, so the image is only there. But here, when we have an RGB image, right, then the RGB image is going to be composed of 3 channels, right? So you have to decide how to apply these filters when it comes to the number of channels. And usually you apply the filters to all of the channel or just some of the channels, or however you decide to do it depending on your application. Usually, yeah, so this is one solution, right? So one solution is to specify one filter for each channel, or another solution would be to specify the same filter for all the channels. Not a big difference here. You just have to be aware of it. So each filter is convolved with a 3D input cube, right? The 3D input cube is X horizontal pixel, vertical pixel plus 3 channels. So then the convolutional core is a 2D mapping, right? And then since we have multiple filters, we have a 3D output because we apply one filter to each of the 2D feature map. Okay. So so you see that, for example, in this case, right, if we have an input which is 32 times 3, and we multiply with 32 times 16, so we have 16 different filters, then the output will be this 32 over 128, right? So it's very easy to grow or to obtain a very large output of these convolutional networks, because, as we said, they are very efficient when it comes to the use of parameters. Sorry. And effectively, when we apply machine learning to a convolutional layer, what we're doing that we are learning the filters, we're learning the coefficients of the filters. So we start with a certain initialization, and then we do backpropagation, and then you can actually go and look at the content of the filters, and you can make sure that, and you can effectively read what the filter is doing after it has been learned, right? So if you have a certain understanding of how these filters work in image processing, as we said, there's some sort of sharpening, some sort of edge detection, some sort of blur, some sort of averaging of the color, averaging of the pixel, then you can go and look at the content of these convolutional filters, if they are small enough, of course, and you can try to interpret what a certain filter is doing in the image. Okay? So then you have to decide your activation function. People usually use a ReLU, right? A rectified nonlinear unit. And this is very simply output is equal to max 0, input. So basically, your input is equal to your output if it's positive, and it's 0 otherwise. The problem with this activation function, of course, is that it has a flat part, right? So when your input is negative, then you don't have a gradient for that area. And so you have to come up with a way of doing backpropagation through this, and people usually do a pass-through estimate for this. Good. Yes, some more. Yes. Now we are here, right? Now we have to decide. So we start from the image. We describe what are the different channels, and now there is this layer that we have to understand, which is called pool feature map. Okay? And this is the operation is called pooling. Okay, let's see this. Let's see what is pool. So the idea is that we want the operation to be invariant to small transition, right? So if we have face, then we know that we have to detect eyes, and it doesn't matter what is the position of the eyes, right? So eyes could be in a certain perspective. They could be closer, they could be further away. So we want to be sort of invariant by that. So the idea is that when we apply filter, right, the output of the filter will produce this matrix. And what we want to do is that we want to do some pooling. And for example, here we want to apply a max pooling, which is we take a certain certain image, and then we see that, and we shift this boy around. So here we see that we have a 2x2 pooling window, which means we start from the left corner, we look at the 2x2 window, and we plot what's inside, what is the maximum value inside the window. Then stride 1, we shift right of 1, and we put what is the largest value, we shift right of 1, we put that, we get an 8. Okay? So the pooling is this idea that we want to take features in an area of our CNN output in order to be invariant with respect to small shifts of our values. Okay, because the kernel will expand, right? The kernel will have this effect of expanding our input, and so now we want to introduce robustness to translation in the input. So here, just to show you how the result changes. So in this case, we have a 2x2 pooling window, and the stride is equal to 2. So we start from this corner with a 2x2. Then we have stride 2, so we move left of 2 and down of 2. And then once we do the pooling, we will plot when we do max pooling, okay, we will plot the maximum value in each of these squares. And so here we'll have a 7, we will have an 8, we will have a 3, and we will have a 4. And here we have a mean pool with 2x2 windows and stride 2. So the way in which we parse the convolutional layer output is still the same, but now we put the average of the values, right? So here we have 4 values, they sum up to 7, whatever. So this is the average values. Okay. Good. So once we have done the pooling, then we can repeat the feature map, blah blah blah. Things continue. So usually the type of architecture that we have is that some convolutional layers followed by some pooling layers, then some more convolutional layers, then some more pooling layers. And at a certain point, the network has to stop. And at that point, we have to take whatever comes out of the convolutional layer or the pooling layer, and we just vectorize it, and then we have to stuff it into a fully connected network. Okay. So yeah, so this is the consideration when you build the CNN. The idea is that you apply a filter to extract some features. Each filter is composed by a small kernel that you shift around according to the stride. After you apply the shifting, then you apply a nonlinear activation function. The parameters are very small because you just have to define the parameters of the kernel and the activation function, the stride, and then you have to decide the padding. When you go beyond the edges, what are you going to do? And of course, you can add some regularization to penalize filters that have very large coefficient, right? That's very understandable. So the input is a 3D cube because the image is X pixel and Y pixel, and then there's a channel for each pixel, red, green, and blue, RGB. And what the output of a convolutional neural network will be also a 3D cube, and each of them would be a certain filter applied to the 2D map. Okay? Then we have the pooling layers. The action of the pooling layers is that of reducing dimensionality. You can extract some specific features from small patches. The parameters of the pooling layers are again the size of the stride window and the size of the window and the stride, and the output again will be a 3D cube, right? So sorry, the output will be a 2D cube, which is the collapsed dimension over which you've done it. Good. Then once you go into the fully connected layers, what you're doing is that you're aggregating the information. You're aggregating the information for each of the pooled parameters, and then you go. What you need to do is that you need to flatten this 3D cube back into a one-dimensional vector, and then the MLP will learn, say, what is the spatial position of the different pixels, right? So since the MLP is fully connected, you don't have to worry about preserving the geometric information in your vectorization, right? So CNN are somewhat spatial, right? So they have a connection to a certain spatial position, right? But once you vectorize them, then if you put them into an MLP, the MLP will learn. And this is a classical architecture. This is VGG. You've never heard of VGG. Remember it because it's one of the core architecture that we talk about. So here you see that you take the original image 224 times 3, and then you have these 224, 64, so 64 channels, and then you see here that you keep repeating conv pool, conv pool, conv pool, conv pool. That's where you get here when you have a 7 by 7 by times 512. Okay, so this is spatially we pull the information down to 7 by 7, but we have 512 dimensions. And now once we have sort of extracted all the 2D dimension down into this 7 times 7 feature and all this and all this dimension in depth, and then what we do is that we do a vectorization. Okay, this vectorization gives us a 4096 parameters, and then we just go down fully connected layer down to our 1000. So this is network we should use for CIFAR 1000, probably CIFAR something, and so we have to do classification of 100 different classes. Okay. So the idea is that each CNN layer learns filters of increasing complexity. Okay, so the first layer only learns basic features, edge, corners, average colors, and so on. The middle layers start detecting part of the object, and then the last layers they're able to recognize full objects. Okay, so if you go and you look at each filter and you put in a set of faces, and then you see what a certain filter learned, you see that so the output of the filter can still be interpreted, right? So because once the filter has been learned, you just apply the filter to the image and you will see what the filter is doing. And you will see that when you have faces, then the first filter recognizes just the direction, then the second filter recognizes eyes, and then eventually you're going to be able to identify faces. With cars are the same, right? You start with horizontal lines, then you process them into lines plus wheels, and then you're going to do same thing, right? Elephant, chairs. This is a classic example of interpretable AI, right? Because you can go into the CNN filter, you can extract the filter, just apply the filter and see what is happening. Good. So just remember the scaling of the parameters. What you have to remember is that the neural networks have a bias, right? So you always have to remember to account for the bias when you look at the parameters. Yeah, just an example of the construction. And yeah, you can go there and visualize what the deep neural network learns. Okay, very good, guys. 2 hours. I think that's all we want to do for today. The class is 3 hours. I don't know how we're supposed to do 3 hours. Okay, so let me stop sharing. If you have any questions, let me know. Otherwise, I'll stop the recording now. So we say goodbye to the people over YouTube. And ciao, ciao.